Quick disclaimer before we get into this presentation. I am an amateur. I am self-taught in many ways in the mathematics, and even with my degree, I do not know about all the names of all these different functions and all that. So, as such, if this function already exists and already has a name, alright, good for whoever named it. But in the end, I don't care. Let's get on with this. Things I'll go over in this presentation are what is the factorial, what is the double factorial, how to generalize into the delta factorial, an integral form for the factorial, how to solve for the delta factorial, breaking tradition and how the delta factorial can be confusing, and end it with a little bit of a fun problem. So, what is the factorial? In general, we know the factorial as being that number multiplied by whatever factorial came before it. When we start off with 0 factorial equaling 1, we then follow with 1 factorial equaling that 1 times all the previous, which is just the 1 from the 0 factorial equaling to 1. Then we have 2 factorial being 2 times the previous factors equaling to 2 times 1, or 2. 3 factorial, the same, 3 times all the previous, being 3 times 2 is 6. That follows along, and then we end up with this functional form for n factorial, being n times everything previous, otherwise written as n times n minus 1 factorial. And we'll save this for another time. So then after that, we can describe what the double factorial is. The double factorial is just similar as the regular factorial, and that it uses all the n times n minus factors. However, with the double factorial, it describes as having each term being separated by 2. So instead of n times n minus 1 factorial, we'll find that for this sequence, we have 0 double factorial being 1, and we'll set 1 double factorial being to 1 here as well. Now, this blue is hearkening to something in the future of this presentation, so make sure to remember that. Now, we go on to 2 double factorial being 2 times everything up above it, which is the 0 factorial. Notice how it skips by that double, that 2 factor. So you got 2 times the 1 equal 2. Then 3, you have the 3 times everything above it. Again, skipping around 2, multiplies by this 1 and gives you a 3. Again, it's in blue, as that may be dependent upon what you learn in the future. Again, we move on to 4 double factorial, being 4 times everything above it, skipping the 3 factorial, and that's just 4 times 2, or 8. This continues on and on until we get the general form for the n double factorial, being n times everything above it, skipping each time, or just in general, n times n minus 2 double factorial. And we will remember that as well as we move on into the next. For the generalized delta factorial, we think about how these numbers are related. For regular factorial, we have n times n minus 1 with 1 exclamation mark as a factorial. N double factorial, see as n times n minus 2 with the 2 double factorial symbol. Continuing on, we as well find that n triple factorial equaling to n times n minus 3 with 3 factorial signs. This continues on and on until we get the delta factorial, where delta is the number of factorial signs that we have in here is equal for the n delta factorial equal to n times n minus delta factorial. Now, that can be quite tiring. We don't want to be writing these delta factorials or these factorial symbols over and over and over again, especially when it gets into larger and larger numbers. So what I'm going to be introducing into here is so-called delta factorial notation. This is just to make everything a lot simpler so that we're not writing all these factorials over and over. Instead, what we can do is just take this period out and represent one factorial symbol with the amount of factorial it is. So for the single factorial, it's 1. Double factorial, it's 2. Triple factorial, 3. Then we can continue on and on and on into n delta factorial, with this delta being represented underneath. Now, not only does this allow us to compact all these different factorial notations, but it also allows us to say about other odd factorials that we couldn't write like this, such as the half factorial, the 0 factorial, the negative factorial, or even the pi factorial. Any number can now be replaced in here, and it can be read simply without having to write down weird negative factorials, whatever you want to try to do to try to make that work. So going back a little bit, we'll talk about how our factorials were created by going integer by integer. But what about non-integer factorials? What about this a over b factorial in here? Well, for that, we have something in the form of an integral. Integral form is nice because instead of having to recursively call on the previous, we can just plug in to this integral form, or n factorial equaling to x going from 0 to infinity of x to the n e to the minus x dx. And for any n, this will work. Well, if you don't count the negative integers, in which case this diverges, but you can just ignore that kind of idea. In essence, you can take this for any n and solve, so even for a over b fractional n's. And that gives us a nice continuous curve. And again, breaking off at the negative integers. So, can we prove that this works? Starting off with this integral form, we want to try to show that n factorial is equal to n times n minus 1 factorial. That was our definition of it earlier. So to do so, we will use integral by parts. Since e minus x is very kind, while x to n can be more complex if you try to integrate it, we'll derive the x to n part and integrate the e to the minus x part. So saying the uv notation for integral by parts, we have xn equal to u, and e to the minus x dx be dv. Derive x to the n and integrate e to the minus x. We have n x to the n minus 1 dx being du, and minus e to the minus x being v. So for integral by parts, wow, uv minus v du. So in order to take that, we use u x to the n times v minus e to the minus x, and you still keep the limits, minus v du. So it's minus n times this integral of x to the n minus 1 e to the minus x dx. Now, some of these things can be very nicely done away with. First, we'll look at this first part with x to the n e minus x. At the lower bound 0, x goes to 0 while e is 1, and that means that we have a full product of 0. And then at infinity, it gets a little bit more tricky because we have an infinity over infinity rule. But you can think about it as e minus x being an exponential decay going much faster to 0, converging much faster to 0 than x to the n is diverging to infinity. That creates this zero dichotomy, dichotomy that says that this upper bound at infinity also goes to 0. So in the end, that whole term goes away. And then just getting rid of the negatives, we have our full term, n times the integral of x to the n minus 1 times e to the minus x dx, which is exactly the form of the factorial that we wanted, with n replaced with n minus 1 multiplied by n. And that is the definition we were looking for. Now that we've seen how the integral form of the regular factorial works, now we can think about how we might be able to generalize it for the delta factorial. In the previous part, we saw that the n was brought down through the power of x, so we might try to keep that. And since we want to change something, we'll go ahead and just try out using that change in the power of e and just writing down, instead of minus x, this f of x in here. So trying that out, you again do u substitution, x to the n being u, and e to the f of x dx being dv. You integrate and derive appropriately to get n times x to the n minus 1 dx be du. And since we don't know the form of f of x, we'll just write this integral as big F of x for now, just to save for later. So big F of x equals v. Then we go uv minus integral of v du. We have x to the n, big F of x at the limits, minus n times the integral of x to the n minus 1, big F of x dx. Now, this is where we kind of have to make a little bit of a leap of faith, in that we want to think that we have successfully created this function in here, such that when we integrate it, it acts very similar to the e to the minus x, in that it exponentially decays and converges to 0 faster than this x to the n diverges to infinity, so that we can properly cancel out this infinite bound here. While the 0, we also want to say that this function is at least a constant a non-infinite constant that we can just cancel out with the 0. So all that being said, we'll just ignore that for now. Then distributing the negative, we have this form, negative n times the integral of x to n minus 1, big F of x dx. Now, we know that we want it in the form similar to how we had it with the regular factorial. And as such, since we know the regular factorial is x times x minus 1 factorial, we want a form for the delta factorial as n times n minus delta factorial, which can be just replaced with the n minus delta in place of this n. Now, we see that since the integral is in the same region, they have the same bounds, and the factor is only off by a negative sign, we can actually set these equal and solve it. Doing so, we have negative x to n minus 1, big F of x, equal to x to n minus delta e to the f of x. Now, if we just want to get this f of x by itself, we can divide by this x to n minus 1. In doing so, have minus big F of x equal to x to the power 1 minus delta e to the f of x. Now, remembering again that this big F of x is the integral of e to the f of x, by deriving, we will get this e to the f of x back. And since on the right side, everything over here is derivable for our notation, we might as well do so. So, taking the derivative, we have minus e to the f of x equaling to the derivative of this right side, or if we use many different rules of derivation. First, we'll take the product rule. We'll take this left function, derive it, multiply it by the right, add it to the left function multiplied by the derivative of the right. So the derivative of this left part will bring down this exponent and then subtract the exponent by 1 to 1 minus delta x to the minus delta, multiply by the right, e to the f of x. Then add it to this left, x of 1 minus delta, and derive it by the right, where e to a function is just e to that function times the derivative of that function. And this looks really nice, because here we have e to the f of x, e to the f of x, e to the f of x. They can be cancelled. Yay! So, doing so, we get this much more clean version. Minus 1 equal to 1 minus delta x to the minus delta plus x to the 1 minus delta f prime of x. Now, all we have that we don't know is this f prime of x. So we'll go ahead and solve for that. Moving this f prime of x over to the left side and everything else over to the right, just keeping everything organized. We have x to the 1 minus delta f prime of x equaling to negative times this whole value of 1 plus 1 minus delta x to the minus delta. Getting f prime completely by itself, we'll derive or divide by x to the 1 minus delta, giving us f prime of x equal negative 1 plus 1 minus delta x to the minus delta, divided by x to 1 minus delta. To get rid of this denominator and make it look more coherent, we'll multiply by its reciprocal of delta minus 1 over delta minus 1, because we can just multiply by 1. That's not a big issue. Doing so, we can find the following form for the derivative of f. F prime of x equals to minus x to the delta minus 1 plus delta minus 1 x to the minus 1, where this delta minus 1 comes from distributing the negative into this 1 minus delta factor. Continuing on from there, we just have a simple derivative form of the function, and we can take the integral. Doing so, integrate, we add to this exponent and then divide by the result. So that gives us negative x to the delta divided by delta. And then this is just a constant times x to the minus 1, which integrates to that constant times log x. So delta minus 1 times log x. And then we need to keep this constant of integration in there. Now we can plug that back in to our form that we had for the delta factorial, with f of x now replaced by this form. You have the integral of x to the n e to the minus x to the delta divided by delta plus delta minus 1 log x plus c. Now, to try to make this a little bit more simple, we can distribute terms and separate the terms out to maybe work with them a little bit more. Since we know log x pairs with e very nicely, we'll go ahead and take out that term, giving us x to the n, e to the delta minus 1 log x times e to the minus x to the delta over delta plus c. Now, as we have this log x term, our log terms allow us to bring this product out front, or not out front, but up above this x as an exponent. We have log x to the delta minus 1, and then the logs will cancel. That just provides us with an x exponent of getting us the integral of x to the n, x to the delta minus 1, e to the minus x to the delta divided by delta plus c. Now, if we get this, combine these two like terms of x into one exponent, the integral of x to the n plus delta minus 1, e to the minus x to the delta divided by delta plus c. Now, we're almost there. All we have is this unknown c. Since this is to be a general form for all delta factorial, we can think of how we can solve this by what we know. And what we do know is the general regular factorial. As the regular factorial is the integral of x to the n e to the minus x dx, we know that is a delta factorial with delta equal to 1. So setting delta equal to 1 in our form, we get the integral of x to the n plus 1 minus 1 times e to the x to the power 1 divided by 1 plus c. Simplifying, we find that this is equal to the integral of x to the n e to the minus x plus c. Now we can match terms. Our x to the n is the same, so we don't have to worry about that. And we have this x e to the minus x plus c equaling to e to the minus x. Now there's no constant term here, so we can conclude our c is 0. With that, we find this integral form finally being n delta factorial, being the integral from 0 to infinity of x to the n plus delta minus 1 e to the minus x to the delta divided by delta dx. That is, but wait, that was small. When we see something in the form of a multiple and a power of the same parity, so even or odd, and we see, not even or odd, sorry, for positive and negative being the delta, and we know that the limits are 0 and infinity, we can think about doing a u substitution, as doing a u substitution with something that is a multiple or a power of the same positive negative parity does not change this fact of the limiting bounds, as long as they're both the same. You can think of this like if we were to take delta as -1, then you would have 1 over delta, giving us these two bounds as minus infinity, or not minus infinity, but 1 over 0 being infinity, and then 1 over infinity being 0. So that would switch those two terms, but then you'd also divide by that -1, which would again allow you to switch the two terms back to 0 and infinity. So if we can do such u substitution, we can simplify this exponent value. So simplifying this x to the delta divided by delta as being u, we also have that x equals to the delta root of delta u. Deriving that, we can get the dx in terms of du as the, derivative of delta u gives us this delta times the derivative of the full function, which it brings out this 1 over delta to the front, and then you get delta u to the 1 over delta minus 1. And that just gets rid of the two deltas. So what we're left with when we distribute the x being this delta root of delta u is the integral of delta u to the n minus 1 over delta plus 1 times e to the minus u times delta u to the power of 1 over delta minus 1 du, where I've gone ahead and taken the liberty of taking out this factor 1 where it's delta over delta when we replace the x with the u. Now we have like terms in here. We have the delta u to the exponents, and we see here we have similar exponent terms as well. We have minus 1 over delta and 1 over delta. Those neatly cancel. Similarly, we have 1 and minus 1. Those also cancel, leaving us with just the integral of delta u to the n over delta e to the minus u du. Much more clean. Now, since we have this delta in here to the power of n over delta, not having any dependence on this variable u, we can just take it out as a constant. Doing so, we have delta to n over delta times integral of u to the n over delta e to the minus u du. Now this is really nice, right? Because this is the exact form of the factorial, with n being replaced with n over delta. So our final result is that delta factorial of n being equal to delta to the n over delta times n over delta factorial. Wonderful. It's just so fun how math can be so simple yet beautiful at the same time. Now, we did take a few leaps of faith to try to get to this form, so we should probably try to prove. How to prove this is pretty simple. First, we'll start off with this exponent, and well, we have n over delta. We'll add a 0 to this with form of minus 1 plus 1. And then as well, we'll take apart this factorial with the rule of the factorial being that x factorial equal to x times x minus 1 factorial. Here this term says that x would be n over delta. So doing so, we have delta to the n over delta minus 1 plus 1, that's 0. And our x, n over delta times the x minus 1 factorial, n over delta minus 1 factorial. Now gathering terms, we'll bring out this n over delta to the front. We'll take out 1 delta with this positive 1 in here. That leaves us with this whole product of n over delta times delta to n over delta minus 1 times the n divided by delta minus 1 factorial. Now we can just cancel out those two deltas. That's nice. Which leaves us with n times delta to the n over delta minus 1 times n over delta minus 1 factorial. Now making this a little bit neater, we can bring these minus 1s with the n over delta by putting it over one denominator of delta. And we know that minus 1 is minus delta over delta. So saying minus 1 to minus delta over delta. We combine it with the n term to give us n times delta to the n minus delta over delta times n minus delta over delta factorial. And this is exactly the same as our delta factorial form with n replaced with n minus delta, providing us with n times n minus delta delta factorial, which is the definition of the delta factorial that we set out to achieve. So we have it. Good. So now let's look at a nice example, the double factorial. So for the double factorial, we set delta equal to 2, and we get this double factorial of x equaling to square root 2 to the power of x times x over 2 factorial. When we look at 0 double factorial, square root 2 to the 0, 0 over 2 factorial, being 1. 2 double factorial, square root 2 squared, times 2 over 2 factorial, or 2 times 1, 2. 4 double factorial, square root 2 to the 4, 2. 4 over 2 factorial, 2 factorial, 2 is, or if I said 2 here, I'm sorry, it's 4. Then 4 times 2, 8. 6 double factorial, 2 to the 6, 8. 6 over 2 factorial, 3 factorial, 6, 48. And those continue on. And we see, indeed, each term multiplies by this n. Now, we get into a little bit of the tricky part. When we plug in 1 double factorial, we find it to be square root 2 to 1 times 1/2 factorial. I'm not going to derive this half factorial or anything. There's so many videos on it and I am too lazy. So instead, I'll just say that this value is square root of pi divided by 2, multiplied by the square root of 2, you get the square root of the full term pi over 2. Now, this is where we harken back to that blue number when we were defining the double factorial. Because when we were defining the double factorial, we just set 1 double factorial being equal to 1. But here we see that this delta factorial function says that it is the square root of pi over 2. Now, we can continue on. 3 double factorial, square root of 2 cubed, times 3 halves factorial, 3 square root of pi over 2. 5 double factorial, 15 square root of pi over 2. 7 double factorial, 105 square root of pi over 2. And indeed, this does follow our laws that we wanted, where each one is the n multiplied by the 2 previous. In this case, instead of having a base of 1, we have the base of square root of pi over 2. Now, this can cause some contention, as there are some other arguments that would suggest that 0 double factorial is also not equal to 1. So, when we think about 0 double factorial not being equal to 1, there is a nice video that I came across just before making this presentation by a guy named Steve from Black Pen, Red Pen. I would recommend you watching his video on that for a more descriptive overview of why 0 double factorial is not equal to 1. I will link this video in the description. But in the end, his argument shows that 0 double factorial may in fact equal the square root of 2 over pi. Now, this looks exactly like the reciprocal of our form for the 1 double factorial, does it not? And indeed, that's exactly what happened in this instance. So, how could we get this? Well, we can get this through the modified delta factorial. The modified delta factorial sets, instead of 0 delta factorial being 1, we'll set 1 delta factorial to be 1. And to do so, all we have to do is divide by 1 delta factorial for the delta factorial function. Doing so, you have delta to n over delta times n over delta factorial divided by delta to 1 over delta times 1 over delta factorial. And that gives us our result for this modified delta factorial, delta to the n minus 1 over delta times n over delta factorial divided by 1 over delta factorial. And you can keep that in mind, but overall, since the more regular delta factorial is simpler, I am choosing to say that that is the natural form, is the general delta factorial form. With that being said, why I decided to tackle this problem is because I actually wanted to solve a different problem and ended up having to figure this out on my own just so I could solve this problem. So I'll leave this with you to solve. Using the tools that we have described here with the delta factorial, you can figure out what is the geometric mean of all numbers between 2 points A and B. You can go ahead and try that out, put it in comments if you want. Let's see how you figure it out. It's lots of fun. At that, I will leave you in this video. Just comment down below if you found this to be helpful or how you think I could improve. I don't generally care for hate, but if you want to actually give me good commentary, I am open to it. Also, you can write down any other exciting facts that you might have found while going through this video or anything you find through using this delta factorial. Anyways, good luck using math. Keep learning.